All right, if you're in a university calculus course, you've definitely heard of the chain rule. And yeah, it's got this reputation for being tricky. But today, we're going to flip that on its head. This isn't just some hurdle to get over. It's the single most important key to unlocking pretty much all of differentiation. So let's dive in.
So here's our game plan. First, we'll talk about why this rule is such a big deal. Then, I'm going to introduce you to something I call the onion analogy. Trust me, it'll make everything click. From there, we'll translate that idea into the official formula, get our hands dirty with some real examples, and finally, I'll show you how to handle those monster functions with multiple nested layers.
Okay, so let's get right to it. Why do we call the chain rule so fundamental? Well, it's because most functions that actually model the real world aren't simple little things like x squared. They're way more complex. Think about the pressure inside a rising weather balloon or the rate of a chemical reaction. These are almost always functions that are nested inside other functions.
And I'm not exaggerating here. This is, hands down, the most powerful tool in your differentiation arsenal. I mean, without the chain rule, we're stuck dealing with only the most basic functions. But with it, we can take on almost anything calculus throws at us. It is a total game changer.
All right, this is my favorite part. This is where it all starts to make sense. Let's just forget about the scary-looking formulas for a minute and use a really simple analogy to make this whole thing feel intuitive.
So this is the core problem, right? This is the question the chain rule was born to answer. You already know how to find the derivative of, say, x squared, and you know the derivative of sine of x. But what on earth do you do with the derivative of the sine of x squared? Now you've got one function stuck right inside another.
And yeah, there's a fancy name for this. It's called a composite function. When you see that f of g of x notation, f of g of x, all it means is that you've plugged one function, g, right into another function, f. And it's exactly this kind of nested structure that needs a special tool to unpack. And here it is. The simple, powerful way to think about this is an onion. Yep, an onion. It's got an outer layer, that's our f function, and it's got an inner layer, that's our g function. The whole secret to differentiating it is that you have to peel these layers one at a time, always starting from the outside and working your way in.
So the whole process really just boils down to two steps. Step one, you differentiate the outer layer. And this is super important, you leave the inside function completely alone for a second. Just pretend it's a single variable. Step two, you then multiply that result by the derivative of the inner layer. That's it. Differentiate the outside, then multiply by the derivative of the inside. That is the heart and soul of the chain rule. Okay, so now that we've got the intuitive onion method down, let's see how this actually translates into the formal language of calculus. And here's the official chain rule formula. But look at it. It perfectly matches our analogy. That f prime of g of x part, that's just the derivative of the outer layer leaving the inside intact. And the g of x part, well, that's just times the derivative of the inner layer. It really is just the math notation for peeling the onion.
All right, theory's great, but you don't really learn this stuff until you start applying it. So let's get our hands dirty and actually see the chain rule in action on some problems you'll definitely see in your course.
Let's start with a classic. Y equals the quantity x cubed plus 1, all raised to the 100th power. So, first, let's identify our layers. The outer function is something to the power of 100. The inner function is that x cubed plus 1. So, we start with the outside. The power rule tells us to bring the 100 down in front, and the new exponent becomes 99. Notice how the inside the x cubed plus 1 is still just sitting there, completely untouched. Now for the crucial part. We multiply by the derivative of the inside. The derivative of x cubed plus 1 is just 3x squared. All that's left is to clean it up. 100 times 3x squared is 300x squared, which gives us our final answer. See? Not so bad.
Okay, now I need everyone to listen up, because this is so important. The number one mistake students make with the chain rule is that they do the first part perfectly, they differentiate the outer layer, and then they just stop. They completely forget to multiply by the derivative of the inside. That little multiplication step is the chain in the chain rule. You absolutely cannot forget it.
And what's so cool is how this rule works for everything. Look at cos of x squared. The derivative of the outer cosine function is negative sine of x squared. Then the derivative of the inner x squared is 2x. Put it together, negative 2x sine of x squared. Or how about e to the sine x? The derivative of the outer e function is just itself e to the sine x. The derivative of the inner sine x is cos x,
So the answer is cos of x times e to the sine x. The pattern is always the same. So you've totally mastered a 2-layer onion. But what happens when you run into an onion with 3 layers, or even 4? This is where the chain rule really flexes its muscles.
Let's check out a problem like this one. Sine of e to the power of 3x. Whoa, that's a function inside of another function inside of yet another function. It looks really intimidating, I know. But the logic is exactly the same as before.
You just keep peeling the onion. The outermost layer is the sine function. The next layer in, the middle layer, is that exponential function, e to the something. And the absolute innermost layer is the 3x. We just work our way from the outside in, one layer at a time.
So really, here's the universal process that's going to work every single time. First, identify all your layers, starting from the outside and working your way in. Second, differentiate that outermost layer, making sure you keep everything else inside it untouched. And third, multiply by the derivative of the next layer in, and you just keep doing that, creating a whole chain of multiplications until you run out of layers. That's the entire game plan.
And just like that, we've taken the chain rule from this scary, abstract formula to a simple, repeatable process of just peeling layers. This is the tool that lets you start to tackle the really complex, interconnected systems you'll find in physics and economics and engineering. So the question isn't whether you can use the rule anymore. The real question is, what are you going to solve with it?